Nathan. I hope you did well on your test. I'm sure you did. I haven't looked at it yet because I know you wanted to check over your algebra, so I don't want to look at it until you've had a chance to look over it. But we're going to start chapter 2 today, and chapter 2 is all about proofs, and I think you're really going to enjoy this. So, chapter 1 was about getting down the basic terminology, basic vocabulary, basic symbols in geometry. Chapter 2 is all about how do you prove something that you might not have known before, and like officially prove it, not just go, well, that makes sense. So it's got some vocabulary that has to go with it. So we're going to start out with if-then statements. That's what section 2.1 is. So suppose you're watching TV and a commercial came on advertising bleach, and the tagline of the commercial said, "For a whiter wash that is out of this world, use Astro Bleach." So what is this commercial implying? It's basically saying that if you use Astro Bleach, your clothes will be whiter. That's what they're implying. Okay. Later that same day, you asked your mom for permission to borrow the car so that you could go to the movies. And she replied, if you clean your room, then you can borrow the car. So what will happen if you clean your room? Well, you'll get to borrow the car. This one, your friends are waiting at the movies for you to arrive. They call you to see if you're coming. You tell them that your mom wouldn't let you borrow the car. What would have led to you not being able to borrow the car? Probably you probably didn't clean your room. Oops. And I know you're probably sitting here thinking, what in the world does this have to do with geometry? It's just the fact that there are logical conclusions to be made from things given certain conditions. And these conditional statements, we like to think of them as if-then statements in geometry. So, like, if I get an A in geometry, then I will get a new car. And I don't know why, but I've always seen it in every textbook I've ever read. They always refer to the if as they use the letter P to stand for it. They'll use Q to stand for the then. So here's some different ways of saying this. Like if you say, so what would happen? Well, sorry, I'm not going to make much sense this morning. I'm way too tired from my trip. Hang on, let me get my coffee. I need to drink a little bit more. Maybe that'll wake me up some. I almost slipped over in the chair just then. That would have been funny to hear about on the video. All right, so the if part, that's your hypothesis. That's what's given. So in this conditional statement up here, the hypothesis is I get an A in geometry. You don't use the word if in there. So it's just like, if what happens? So if this happens, then what's your conclusion? It's I will get a new car. Again, you don't use the word then. That's what the P and the Q are. So the hypothesis is in this statement is that you get an A in geometry. The conclusion is you get a new car. We say that a lot of times we actually do an if-then statement. So if this, then that. Or you can say that P implies Q. So if I get an A in geometry, that implies that I will get a new car. That is what this says. This is like a notation way of saying P implies Q. So you've got the arrow pointing to the right. So like this thing leads to this happening. Okay. Conditional statements are not always written with the if clause first. But I'll be honest, I think when you're doing the geometry with it, I think it is helpful to rewrite it that way. So, like for this next one, I will give you a ride home if you give me gas money. So what is the hypothesis? It's that you give me gas money. And what will that conclude? Like, what's the conclusion? What will be implied by that is that I will give you a ride home. But again, it's helpful, I think. It's like, if it's rewritten, if you give me gas money, then I will give you a ride home. Okay. This next one, if x squared is equal to 25, then x is less than 10. So the way you'll see that, if p then q, that's this one. So if x squared is equal to 25, then x is less than 10. You'll see p implies q, so x squared equaling 25 implies that x is less than 10. This one, I hate this one. I really do. I'd never use it. I think it's confusing. So it'd be like x squared equals 25 only if x is less than 10. But like I said, I think that one's worthless. I think it's, I don't know. I think people have to think about this way too much. So it does, so I guess I'll put that. X squared is 25 only if x is less than 10. But again, I'm going to avoid that one because I think it's confusing when people read it. And then you could also say q of p. So x is going to be less than 10 if x squared is equal to 25. Okay, now the converse of a conditional statement, that's when you swap the hypothesis with the conclusion. So if p then q becomes if q then p. So a statement and its converse can say totally different things. They do not have to say the same thing. They don't have to both be true. So, here you go. Sorry. So it may be a true statement to start with, but when you turn it around and you say it's converse, that makes it false. So let's get to some of these. So a counterexample, just so that we can figure out if it's true or false. A counterexample is any kind of just words or a diagram or something that proves that if the statement's false. Hang on, I got blood in my nose. Ugh, my allergies are acting up. Sorry, Ethan. Okay. So we say that an if-then statement is going to be false if we can find a counterexample. A counterexample is an example where the hypothesis is true, but the conclusion is not. So, and obviously, I lived in Indiana when I made these notes up. So if I live in Indiana, then I live in the United States. All right, so that is a true statement. So if you live in Indiana, then you live in the United States. The converse of that, though, so let's go through this. So the hypothesis in this one is I live in Indiana. The conclusion, oop, I got an email. Can you hear the email thing ding to tell me I got one? I don't know how sensitive this microphone is. Oh, speaking of which, I've got it in the case. I just realized that. I don't know if I'm covering up the microphone. Ugh. So let me know, tell me at the end of class if it sounds better now than it did just a minute ago. Because I just took it out of the case because I don't know that there's good access to the microphone if it's in the case. If you could hear it just as well 5 minutes ago as you can hear it right now, let me know that, because then I'll just leave it in the case. But if you can hear me better like this, then I need to take it out of the case every time. Okay, so the conclusion here would be I live in the U.S. So the converse is when you swap places with the hypothesis and the conclusion. And I had a kid one time that said that the reason they remembered that was Converse is shoes and you can put them on the wrong feet. And I thought that was kind of funny. But anyway, so the converse would be if I live in the United States, then I live in Indiana. So that's obviously false because we can find a counterexample. The counterexample is I live in Alabama. So you're meeting the hypothesis. You live in the United States, but you do not. It does not lead you to the correct conclusion according to the converse. So this would be an example of one where the original if-then statement is true, but its converse is false. Some statements, though, have true converses. So like if I told this one, if today is Wednesday, then tomorrow is Thursday. Where my hypothesis is today being Wednesday, the conclusion is tomorrow being Thursday. So the converse, if I swap places with the if and the then. So it would be if tomorrow is Thursday, then today is Wednesday. Okay, so this is one where the original conditional statement, the if-then statement, is true, but the converse is also true. Okay, so we call these where both the original statement and the converse are true, we call those biconditionals. So when a conditional and its converse are both true, we can combine these into a single statement using the words if and only if. So since it's true both ways, like up here, we could just say today is Wednesday if and only if tomorrow is Thursday. So when you see this, it works both ways. So with the arrows, we would point both directions. So P implies Q and Q implies P. There is a shortcut. Instead of actually writing out if and only if you see somebody write IFF, they're not misspelling the word if. They're a mathematician and they know that that means if and only if. So that's a short way of saying if and only if. Okay. So every definition that you learn has to be a biconditional. So if it's a definition, they're all biconditionals. Here's some different definitions. Like definition of a congruent angle. Congruent angles are angles that have the same measure. So the conditional of that, it's saying like, okay, if angles are congruent, then they have the same measure. So we could say that. But we could also say if angles have the same measure, then they are congruent. So the biconditional way of saying that would just be that angles are congruent if and only if they have the same measure. Okay, all right, so here's some examples of like what you're going to have to do today. So the distance from V to W equals the distance from X to Y implies that the segment VW is congruent to the segment XY. Okay, so basically what that's saying is if VW equals XY, then, that does not like a V, is congruent to XY. So the hypothesis would be this. The conclusion, I can do that, would be this. The converse would be me turning it around. If that is congruent to this, then this is equal to that. All this is true because it's a definition. That's the definition of congruent segments. So, oh, this spread out weird. Sorry, that was supposed to be on the next page. I didn't catch it when it downloaded it, moved things around. So sorry these are on weird pages like this. So I'll dive if you dive. So I just think it helps to make it an if then. So if you dive, then I'll dive. So the hypothesis is that you dive. The conclusion is that I'll dive. And the converse is if I dive, then you'll dive. Okay. Don't know if that's true or not. Here's the next one. If A equals B, then A plus C equals B plus C, which is true. So the hypothesis, A equals B, because it's written as an if then, which is helpful. The conclusion is that this is true. The converse is if A plus C equals B plus C, then A equals B. So it's just doing a lot of vocabulary and getting used to the terminology. So provide a counterexample to show that each statement in numbers 4 through 6 are false. So again, sorry about how this is. It printed to OneNote this way. I'm hoping it's on your paper a different way. If it's, hang on, let me look. Did I print your notes out yet? Oh, I haven't printed them out yet. I can fix this then before I print them, so that's good. Provide a counterexample. So these two segments being congruent, and oh, this was on your quiz the other day that we talked about. So what's a counterexample that makes this an untrue statement? I mean, it could be true. This is not the counterexample. So if here's A, here's B, here's C, and AB is congruent to BC, then yeah, there B is the midpoint. That's not the counterexample. Here's a counterexample. Can you find just one example where this does not lead you to that? And sure, that's congruent to this. And B is not the midpoint. So you would have had to have said that B was between A and C along with that for it to have actually been a true statement. So this is an example of a counterexample. Provide a counterexample to show why this is false. If a number is divisible by 4, then it's also divisible by 6. How about 8? That's your counterexample, because 8 is divisible by 4. 8 is not evenly divisible by 6, though. So that's 1 1/3. So 8 would be a counterexample. If x squared is equal to 49 only if x is 7. Oh, and this is the one I said I wasn't going to use. And then it's in the notes still. Wait, where was it? We said that. I'm making you dizzy, aren't I? Yeah, the whole only if. Because what this means is if x squared is 49, then x is 7. But we know that's false because x could be negative 7. And negative 7 squared is still 49. But again, I'm trying to think why I left this in there. It's probably just because of the fact that we wanted to throw 1 in there for the notes, even though I remember me and the other 2 ladies who taught honors geometry, we decided that we were getting rid of all those because we think they're confusing. Okay. So state the converse of each conditional for problems 7 through 8. Is the converse true or false? So if a number is divisible by 6, then it's divisible by 3. So its converse would be if a number is divisible by 3, then it's divisible by 6. All right, so is that true or false? False. Because 9 is divisible by 3, it is not divisible by 6. So it's a false statement. Oops. And this would be a counterexample that can prove why it's false. Okay. So x equals 3 if 6x is 18. So let's write it as an if then. So wait, let's do this. This is the converse. Like, I was ready on this one because it started out as an if then. This is just me rewriting this statement. So this is just my conditional. So if 6x equals 18, then x is 3. All right, so the converse would be if if x is 3, then 6x is 18. And that's true because of the multiplicative property of equality. If I multiply both sides of an equation by the same thing, it's going to be the same thing. And you're going to end up working section 2.1, the written exercises, page 30. It's going to be page 35. You're going to do numbers 1 through 5, all of them. 7 through 23, all of them, and 26 through 30, all of them. So that's going to be what the homework's going to be. Well, I don't guess, technically we're probably not giving you homework because you work fast enough, like what you're doing in class is enough. So if you ever do want some extra stuff, we can do some math team kind of stuff for homework. So you just tell me what you think about that, because I know you're going home and just learning stuff on your own because that's who you are. So if that's enough to keep you busy, then that's great. If you'd like to start working on some math team stuff along with this, I think that's awesome. And I'd probably, this week's going to be chock full of just getting notes and stuff ready for you. But this weekend, because I've got the holiday, I'll have an extra day to work. I can start sorting through math team stuff and getting things ready for you. Okay.